All right, let's do this. Okay. So welcome to the review for exam numero dos. So, just quick announcements. So obviously the exam opens up tomorrow, so make sure to keep that in mind. And it closes next Tuesday. Yeah, next Tuesday. And then the exam extra credit 3. You have until tomorrow morning at 9 p.m. to take care of that. So that's basically do some problems from the challenge packet, basically. So if you have not had the chance to do that extra credit, please do so, because it's 2 extra credit points. So that, and it's more a review for the exam. So kill 2 birds with 1 stone, yeah? So. And then on top of that, Zoom office hours tonight from 6 to 8 p.m. for any last minute questions, or if you want to just say, hey, I have my work, I don't want to email to you, so here, I'm just going to put it over Zoom. I can do that, and I'll have my screenshot ready to go. I can screenshot your work and call it there. But past that, that's all I really had. So now, like I said, like we had with the exam 1 review, you guys can. It's basically centered around you guys. So on all 6 of you. So who has questions?
Was there a review package posted for exam 2, like on your website? Because I couldn't find it.
There were 2. So if we hearken to that. For those watching online, I apologize, but you can go ahead and just pull up my webpage for those that are looking at it. So they're right here.
Oh, okay.
So here are my challenge problems, and here are the ones straight from Long Kappa. So, okay.
And the challenge problems are the extra credit ones?
Yep, challenge problems are for the extra credits. Okay. And I sent some details about how to get credit for that in an email on Monday, so please make sure to take a look at that for the rules and regulations, so to speak. Okay. Alright, so who has any questions on anything?
Well, this is like a math problem, but I wasn't able to access the homework last night. Like on Long Kappa, I would go to content and then homework, and like the drop-down arrow would go down, but nothing would be under homework.
Huh. Weird.
That was at like midnight last night. I haven't tried to check today.
Yeah, I think they may just had some like syncing issues late last night, so maybe that's why. I'm not sure, because I can access Long Kappa right now just fine. So
Okay.
that could have just been a late night syncing thing.
Yeah.
So okay, any others you guys want to take a peek at? Anything from the challenge packet? Anything from the Long Kappa packets? Any lesson problems you guys are like, what the heck is this, what's going on right now?
Can you go over example 19 from the review?
Yes, the example 19. From this one, the Raider problem? Okay. Okay, anyone else have any requests? What's up?
C.
What's that?
8C.
8C. Okay. So 19, 8C. Okay. Okay. So, okay. What I think I might do then, I think I'll do that those 2, and then I was thinking about doing this one as well, 1D, because that one's pretty advanced, or I'll do a variant of it, I guess I should say. So, but I'll do that one, and then I will do example 7, unless anyone has any other requests on anything. All right. Give you guys an extra minute or 2 to find something, unless y'all have any pressing questions. You're like, I need to understand this. And I don't. Did you have any questions you wanted to look at, or anything you wanted to think of? Okay. Okay. Okay, so let's go ahead and let's get down to business. Okay, so let's see, what did I do for this one? All right. So what I'm going to do, first example. Okay. So I'm going to do example 1. So we're given this weird obscure function, y equals the natural log of the 5th root of 2x minus 1 divided by x to the 4th plus e to the x squared. And basically, we're asked to differentiate this, essentially. Now, the thing is, I'm not sure if the exam is going to be nice and do this to you, but I'm going to do this here. I'm going to give you a hint. If you see something natural log and you see anything like this, try to use natural log properties when you can, because that will make your life incredibly less stressful. So use log properties when possible. Okay? Now, of course, I can't guarantee that the exam will be this crazy, but I'm also not sure if they won't. So I guess it's the best way I can say it. So figure cover all the bases, and then we'll go from there. So what we'll do is let's go ahead and say, all right, well, what are these log properties I'm talking about? Well, let me tell you. So natural log of a times b is equal to natural log of a plus natural log of b. So that's numero uno. Numero dos is a divided by b is natural log of a minus natural log of b Numero drei, for those that know some German, is b times natural log of a. So third property is this. And then number 4, d over dx of natural log of x equals 1 over x. So that's number 4. Okay, so those are the 4 big properties you'll need to know regarding natural log stuff for the exam. So you might think, okay, well, that's fine, but why should we care? Like, how does this help us here? Well, the thing is that these help us to make our life significantly easier, because if we were just essentially asked to find the derivative of this, that's quite a nasty thing to differentiate, and I really hope they don't give you this on the exam, because that would be quite disgusting to differentiate. So thankfully, yeah?
I was just going to say, well, you could pull that out, like, all the way.
Yeah. Pull what out?
How you could use the ln natural log laws to, like, expand that.
Yeah.
Yeah.
Yeah, I was actually going to get to that. But thankfully, we have natural logs, so we can use these properties to make our lives significantly easier. So, in this case, we say, all right, the first thing we notice is that we have this natural log of the 5th root of something. So, using the appropriate property, how can we simplify this?
You bring up with that to the front.
Yep. So we get 1/5 times natural log of 2x minus 1 over x to the 4th plus e to the x squared. Okay? Okay? And then what we notice is that now we have natural log of some fraction. So using the appropriate property, let's just say that this becomes what? So we get 1/5 times what?
We use the second property.
Yep.
So would it be ln 2x minus 1 minus ln
would be 1/5 over here as well, but yeah, right idea. So then 1/5 times natural log of x to the 4th plus e to the x squared. Okay. So unfortunately, this is all we can really do because now we have just a difference and a sum in both of these natural logs, so that's all we can really do. So now let's go ahead and differentiate this thing. So the nice thing is that if we want to differentiate this, well, we can differentiate this term by term. So that's one thing that makes things a bit nicer. And on top of that, if we have a constant hanging out here, all we need to do is essentially say, all right, if you want to find the derivatives of these two terms, take the derivatives of these two first, and then multiply 1/5 after that. So in other words, we have 1/5 times the derivative of natural log of 2x minus 1 minus 1/5 times the derivative of natural log of x to the 4th plus e to the x squared. Okay? Alright, so now what that says is that we have 1/5 times the derivative of natural log of 2x minus 1. So what does that equal here?
Is it 1 over 2x minus
Yep, so that's part of it. So we have 1 over 2x minus 1 times what? 2, right. Because remember, if we apply the chain rule roadmap, we have, all right, so the inner function g of x in this case is 2x minus 1. The outer function is f of x equals natural log of x. So what that tells us is that, well, f prime of x, as we just established, is 1 over x. So as a result, f prime of g of x, well, you just replace x here with whatever g of x is. So we have 1 over 2x minus 1. But then, well, g prime of x is just 2. So all we have to do now is just multiply these two things to get the desired derivative of that. Okay. So then, employing similar reasoning on the second derivative yields, all right, so this is going to be 1 over x to the 4th plus e to the x squared, and then essentially times the derivative of whatever this is. So derivative of x to the 4th plus e to the x squared. Okay? So, if we clean this up a bit, we notice, all right, this is just 1/5 times 2 over 2x minus 1. And then we have minus 1/5 times, well, x to the 4th plus e to the x squared. And then, so on the numerator, we just have this derivative here, which is just what?
4x cubed plus 2x to the x squared.
Right. Okay. Because derivative of x to the 4th is 4x cubed because power rule, and then you apply chain rule on e to the x squared to get 2 times x times e to the x squared. Okay? And that will be your answer for example 1. Okay?
For e to the x squared, like how would you apply a chain rule on that? Like, what would the inner and outer function be?
So in this case, one way you can think of this is to think of e to the x squared as, you can think of this as like exp of x squared, is one way you could sort of think of it. So in this case, your inner function, so g of x in this particular case, bless you, would be x squared, and f of x would be e to the x. Okay, and then, so that way this sort of gives you an idea of, how you can sort of visualize what's going on with chain rule here. Okay.
And just, f prime would just be e to the x because derivative.
Exactly. Okay. So any other questions on example 1? Okay, cool. Alright, so then the next one I want to look at is example 7 from the review packet. So example 7. So what we're doing here is that we're saying, all right, let me see if I can find my notes on this. Okay. So what example 7 says is that, so position function, so position in feet of an object moving on a line at time t in seconds is we're going to denote that by s of t equals t cubed plus 4t squared plus 5t plus 12. Okay? And so the goal of this problem is we're going to focus on find acceleration when velocity is 8. Okay. Okay. So before we move into this question proper, let's do a quick little recollection of some concepts. So if we have some function s of t, if this is a position function, does anyone remember what the relationship between position and velocity is?
It's the derivative.
Right. So if you differentiate position, you get velocity. And then from that, well, what happens if we were to say, what's the relationship between position and then acceleration?
Acceleration is the second derivative.
Right. So we have to take two derivatives to get the acceleration. So we will denote the velocity function by v of t, and then a of t is our acceleration function. Okay. So using these two properties here, we can say, all right, a quick little application of power rule, or I guess several applications of power rule, will yield that v of t and a of t both will equal what?
You have to do 3t squared plus 8t plus 5.
Yep. And then a of t?
6t plus 8.
Yep, 6t plus 8. Good. Okay. Alright, so now what we have from this is that, alright, so if v of t is equal to, we're trying to figure out the time when velocity is 8, so then that way we can say, alright, well, we need to find the acceleration at the time when velocity is 8. So, in this case, let's go ahead and say, all right, well, when is our velocity equal to 8? So, when is v of t equal to 8? Okay. So, that implies that we should set this quadratic here equal to 8. So we have 3t squared plus 8t plus 5 equals 8. So what that says is that, all right, we have a quadratic with a quadratic term, a linear term, and a constant term. So that means we're going to need to make sure everything is on one side. So we have 3t squared plus 8t, and if we subtract 8 over to the other side, we just get minus 3 equals 0. Now, on the surface, it's not immediately obvious what the factorization of this should be. So what's our sort of last resort in this case?
The quadratic function.
Quadratic formula, but right.
Formula, yeah.
Yep. Okay. So then in this case, let's go ahead and apply that. So in this case, we have, all right. So in this case, t equals, let's see. So t equals negative 8 plus or minus the square root of 8 squared minus 4 times a, which is 3, times c, which is negative 3, all over 2 times a, so 2 times 3. Okay? So what happens is that, all right, well, we have negative 8 plus or minus something over 6. So if we try to simplify what's in here, we have 8 squared minus 4 times 3 times negative 3. So when we could think of this as just 8 squared plus 4 times 3 times 3. So if we plug this into a calculator, what would the simplification of this expression inside the square root be? It used to be 100, right? So what's nice about that is that this is just negative 8 plus or minus 10 over 6. So that means, okay, break this up into our two solutions. So we have negative 8 minus 10 over 6, and then negative 8 plus 10 over 6. Okay? So as a result of this, we say, all right, this is just negative 18 over 6, so negative 3. And then this is just 2 over 6, or 1/3. So our two values of t here are going to end up being these two. But, oh, wait a minute. Remember, with these types of problems, there's a bit of a caveat. So if you remember, that caveat says, okay, we have to start at time t equals 0 for our system here. So what that means is that the particle starts moving at t equals 0. So in this case, our domain is t greater than or equal to 0 with these types of problems where you have position, velocity, or acceleration. So as a result, well, negative 3 is out, and your only option is 1/3 as your only valid time. Okay? So as a result, well, now that we have the time when velocity is 8, let's go ahead and find the acceleration at this time. So we have a of 1/3 equals 6 times 1/3 plus 8. So a quick little bit of algebra should then tell you that this is just equal to 10. So, and that will be your answer here. Okay. So any questions on example 7? Okay. So now moving on to the next example, we have example 8c. Or is anyone still writing this? Okay. Right. So, example 8c. So find dy over dx for cotangent of x cubed times y equals y to the 4th. Okay? So what you'll notice is that this is going to be a sort of implicit differentiation problem, because what you'll notice is that we're given dy, we have to find dy over dx if we have this equation here. So if you recall, there's sort of that asterisk rule that I brought up from lesson 14. So I'll go ahead and bring it back up here. So treat y as a function of x. So if you remember from implicit differentiation, we always have to let y be some function of x. We don't know what it is, but all we know is that x and y satisfy this relationship. We don't know what y is, but that's all we know. So what that says is that, all right, if you remember that rule, we had d over dx of f of y. Well, that was just f prime of y. So you take the derivative of this thing like you normally do, but then because of chain rule, you got to multiply dy dx into there. So that was that asterisk rule that I brought up at that lesson. Okay, so as an example, if we were to say differentiate y to the fourth, then we have d over dx of y to the fourth. So if we apply this rule, well, if we apply this rule on y to the fourth, then what should you get out of the results? So in this case, f of y is just y to the fourth. So in this case, you apply the derivative like you normally do, so 4y cubed. But then because of chain rule, you have to multiply dy dx into there. So that gives us the right-hand side of our equation here. So now all that remains is to figure out what's going on the left-hand side. And that's where things get a bit trickier, because we have cotangent of x cubed times y. So what you'll notice is that we have x cubed times y, so we have a product of one function of x as x cubed times another function of x, which is y here. And all this product is contained entirely within a cotangent. So what that says is that we have one function of x, so one function of x inside cotangent. So because of that, what should that tell us about what derivative rule we ultimately need to use here? Like, what's sort of the biggest rule here of the three? So product, quotient, or chain rule?
Chain.
Chain rule. So ultimately, use chain rule. Okay. Okay, so if we do that, we say, all right, well, as we sort of established already, g of x as the inner function is just x cubed times y. But then f of x is just cotangent of x. So outer function. Okay, so let's start with the outer function for starters. So does anyone remember the derivative of cotangent?
Is secant squared times x squared?
Kind of on the right track, but not quite. So what could you repeat that again?
Is it secant squared times x squared?
Not quite. So like I said, right track, but not quite. Does anyone remember? Okay. So basically the derivative was negative cosecant squared of x was your f prime of x. Okay? So as a result, f prime of g of x, well, all we have to do is just replace x here with whatever g of x is. So we have negative cosecant squared of x cubed times y. Alright? So that takes care of f prime of g of x. So now let's go ahead and deal with g prime of x. So how do we deal with that here? So like I mentioned, we have x cubed, one function of x, times y, another function of x. So what's our rule going to be here if we want to differentiate this? How are we going to handle that?
Product.
We got to do a product rule, right? So while chain rule is ultimately the biggest thing happening here, we have to do a product rule inside of all this. Okay? So what that says is that, all right, we have x cubed times the derivative of the second function, so d over dx of y, and then plus derivative of the first, so d over dx of x cubed times the second, so y. So, because of this, if we were to go ahead and try and clean this up as much as we can, then what would this simplify to? So, first term would be x cubed times what?
Just one.
Well, 1 times
That'd be one.
d over dx, right? So in this case, we just have dy over dx on the first term. And then on the second term, we have what?
X squared y.
Yep, 3x squared y. Good. Okay, so now that we've got all our chain rule and stuff taken care of, what that says is that, all right, that means our derivative that we're ultimately trying to find is just the product of these two things here, right? So we have negative cosecant squared of x cubed times y times x cubed times dy over dx plus 3x squared times y. Okay? So this is the left-hand side, this is the right-hand side, so now we just equate these two. So we have, ultimately, negative cosecant squared of x cubed times y, x cubed times dy over dx, plus 3x squared times y, equals 4y cubed times dy over dx. Okay. So now, fun part is trying to clean all this up. So, one thing we can do here is say, all right, well, let's make our lives a bit easier and go ahead and distribute this cosecant squared into both terms here. Just one thing we can do. So in regards to like what log kappa what happen on log kappa, so one of the things I kind of did with this example is I kind of like just made an example like this. So I'm not sure if that's going to happen on the exam. I kind of just made this up just to give us some practice. So what we could do is just say, all right, well, if we just want to solve for dy dx, then one thing we can do is just distribute the negative cosecant squared into both terms. So we have negative x cubed times cosecant, if I can spell today, cosecant squared of x cubed times y times dy over dx minus 3x squared times y times cosecant squared of x cubed times y equals 4y cubed times dy over dx. Okay, so now what we can do is say, all right, if we want to solve for dy dx, one thing that might help is to bring all the terms that have dy dx in it into one side and leave all the remaining terms on the other. So in this case, well, the easiest thing we can do from that is just add this term over to the other side. So ultimately we have 3x squared y times cosecant squared of x cubed times y of 4y cubed dy dx plus x cubed times cosecant squared of x cubed times y times dy over dx. And the nice thing is, since both terms here have dy dx in them, we can just rewrite this as 4y cubed plus x cubed times cosecant squared of x cubed times y all that times dy dx means. Okay. All right. So then a quick little bit of division later should then give you dy dx, which is then just, well, the numerator as 3x squared times y times cosecant squared of x cubed times y divided by 4y cubed plus x cubed times cosecant squared of x cubed times y. And that's that example. Yeah, like I said, these were intended to be on the challenging side, so yeah, I was not kidding with that. So, any questions on any of that? Okay. Yeah. But like I said, I'm not going to guarantee that these are going to be this difficult, but I'm just doing this so that way you guys have more practice. So, if they do happen to be that hard, well, now you have practice doing so, but now if they are a lot easier than this, well, yeah, now you've had to practice in doing harder problems. So, like I said, these are good, like, practice problems, but good exam problems, that's a bit debatable. But, yeah. Anyways, so that's that. Okay, so last example that we want to talk about, and that was also requested, was the related rates problem. There you go. Okay, so the last example I want to do is this related rates one. Okay? So, the premise is that we have this radar seeing a UFO flying away at the speed of 450 miles per hour at an altitude of 4 miles. And the question is, how fast is the UFO's distance from the radar increasing the moment the UFO flies over a point on the ground 7 miles from the radar? Okay. So for the person that asked to do this problem, did you want to look at both parts, or do you want to just do one of them? Or is there one you were looking at more at?
More the second part.
Second part? Okay. Then we'll take a look at that one then. Okay. We'll do that one first, and then we have time. We can do the first part. Okay. So the problem states for the second part, we have to find the rate at which the angle of elevation decreases when the angle is pi over 6. So what we're going to do is we're going to say, all right, we're going to let z here be the actual distance between the radar and the UFO. We're going to let y be the altitude, and then we're going to let x be the distance between the radar and then the point on the ground where the UFO is above it, or below it. So this point right here. All right. So what that says is that since we also have to put up with an angle of elevation, well, that means we're going to need to introduce an angle theta here. So ultimately, we have this right triangle we have to consider here. All right. Now, if we had, say, if we did not have to deal with this angle at all, i.e. if we were focusing on part 1, then if we recall that 5-step process that we did for related rates, the first step was identify the needed formula. So in the first step of part 1, we would have x squared plus y squared equals z squared. Would be the formula we need for that. But with part 2, well, since we have to put up with an actual angle, it's not immediately obvious what equation we have to use. So for this one, we're going to need some trig function. We need trig, and we're going to use one of the SOHCAHTOA formulas. But we got to figure out more data to figure out which of those 3 we need. So for part 2, we say, all right, remember, step 2 says we have to identify which of these 4 of theta, z, x, and y, which of those were constant and which of them vary with time. So which of those four variables vary with time and which don't change? So if we take a look at the problem, the UFO is flying away at a speed of 450 miles per hour at an altitude of 4 miles.
Would Z and X be bearing and Y remaining constant?
Yep. So y is the only thing that's going to be constant here. So y is constant, and specifically equals 4. All right. So now step 3 says, all right, we have to focus on what's given to us at a specific point in time. At point in time. So given, we have to say, all right, what other data are we given here that's not constant? So the problem says we have to find the rate at which the angle decreases the moment the angle is equal to pi over 6. So that should pretty quickly tell you that the angle theta is just pi over 6. So based off of our data, the only number left that's not this, because that's just a meme at this point, is the only one left is this 450. So the UFO is flying away at a speed of 450 miles per hour in the horizontal direction, so in this direction here. So if that's the case, what rate would the 450 correspond to? dx/dt, right. Right? So we're given that, and we need to find what? So we need to find the rate at which the angle decreases. So that should pretty quickly tell you that we got to find d theta dt at this specific point in time when theta is pi over 6. So what that tells us is that we already have y given to us. So we need one of the trig formulas that deals with theta and y because it's constant. And then because we're given dx dt, that means we also need to put up with x as well. So we need to deal with the trig equation using x, y, and theta. So what trig equation can I think of that deals with these three variables and using SOHCAHTOA? Tangent, right? So we have tangent of theta equals, if you recall, SOHCAHTOA, opposite over adjacent, so y over x. But the nice thing is, y is constant, so that makes our lives a lot easier here. So ultimately we have 4x to the negative first equals tangent of theta. So that's ultimately the equation we've got to use here. So, okay. So now, let's go ahead and differentiate this with respect to time t. So what you'll notice is that this is going to be very similar to what we've done in implicit differentiation, but now we have to differentiate this equation here with respect to t. So what we're saying with this is we have to treat x and theta both as separate differentiable functions of t here. So let's x and theta be differentiable functions of t. Okay? So, if we do that, that means we're going to need to employ that sort of asterisk rule I brought up earlier. And by which I mean in this case we have d over dt of f of, say, some function x. If we differentiate this with respect to t, then we're going to have f prime of x times dx over dt. So in this case, like we had before, differentiate f of x like you normally would, but then because of chain rule, you've got to multiply dx dt into that. And then a similar equation holds if you replace x here with theta. So, okay. So using that reasoning, we have differentiating 4x to the negative first equals tangent of theta with respect to t would yield what? So if we differentiate 4x to the negative first with respect to t, what should we end up with here? Using this rule.
Negative 4x to the negative second dx over
Yep. Times dx dt. And then do a similar thing with the other side, and replacing x with theta gives us what?
secant squared theta d theta.
Right. Okay. So here's what we have here. So we have, all right, we got dx dt, that's good. We have theta, so we can ultimately figure out what secant squared of theta is. And we have d theta, we're trying to find d theta dt. But, oh, wait a minute, we don't have x though. So how can we figure out what x is from this?
You can use a trig function against one of the other numbers. So yeah,
Right.
solve for x in that situation.
Right, so in this case we already have what theta is, so we can just plug a theta into here to get the corresponding x value from this, right? So if we do that, so we have 4 divided by x equals tangent of pi over 6. So does anyone remember the value of tangent of pi over 6 from the unit circle?
Is it 1?
It's not 1, I think you're thinking of pi over 4.
What does this mean, 0?
It's not 0. No, okay, I think I'll just go ahead and say it. So it's 4 over x equals 1 over root 3. So yeah, make sure you review the unit circle in that case. So, okay. So as a result, a quick bit of algebra later should then tell you that this is just 4 times the square root of 3. Okay. So then now that we have all that, we can go ahead and plug this into our data here to figure out what d theta dt is. So we have negative 4 over, well, 4 root 3 quantity squared times dx dt, which is 450. And then secant of pi over 6 quantity squared times d theta dt. So what I'll say from this is that I'll sort of just say, recall that. So remember, does anyone remember cosine of pi over 6? Okay. All right, so I'll just go ahead and say that it's root 3 over 2. So since secant is 1 over cosine, you should have 2 over root 3. So that's going to be your expression on the right-hand side. So ultimately, you have negative 4 times 450 over 4 times root 3 squared, so 16 times 3. And then this equals, well, 2 over root 3 squared, so 4/3 times d theta dt. And what you'll notice is that, oh, wait a minute, we have a factor of 4 on both terms in each side, so they cancel out. And then 3 on the bottom of each term on each side, so those cancel out. So ultimately you're left with d theta dt is equal to negative 450 over 16. Okay, so that's part 2. So any questions on any of that? Okay, well, okay, so I guess we only have like 10 seconds left, so that's all I can really do for today. So I apologize for not being able to do the first part, but yeah, like I said, part 1's a bit simpler, a lot less trigonometry involved.